Hello, hello. We are here. This is very strange to be seeing you guys. Good morning, good morning, good morning, good morning. Okay, hold on. Good morning, Alyssa. Good morning, Daniela. Good morning, Jayla. Good morning, Sawad. Good morning, Charlie. Good morning, Noel. Good morning, Vivian. I'm doing this. Did I say Alyssa? Okay. Good morning, Daniel. Okay. Good morning, Vivian. Or did I say that? I'm sorry. Yes. Okay. Good morning. And give me 1 second. You know what's strange is that without the board, I don't see the actual time. Okay. So the board is coming. Give me 1 second already, but it's good to see you. Did I say good to see you, Soad? Good to see you, Vivian. Good to see you, Charlie. Good to see you, Noel. Good to see you, Jayla. Good to see you, Alyssa. Good to see you, Daniela. Or Daniela just froze. That's weird. Okay, but hold on. Let me. Oh, and good morning, someone who's coming right now. Farouk. Okay, hold on. The board. Something is happening with my board. Just give me 1 second. What is happening? Oh, we have an internet. And I'll tell you what. Wait, and someone is here. Okay, we're going to start in a second. But there seems to be something going on with my internet. Quick question, while my internet is doing something weird, not my internet, I shouldn't say that. While my connection in my to the internet is doing something weird. It's like, I always hate when people say like, well, then I'm going to turn 22 and then I'm going to get my degree and then I'm going to get my bachelor's and then I'm going to do this and get a job. And I'm always like, wait, if you haven't gotten your bachelor's yet, why is it yours? What do you mean you're going to get your bachelor's? Why don't you just get a bachelor's? Like, it's not yours until you get it. What are you talking about? But all right. So what am I talking about? I'm talking about that I'm having an internet issue. I'm stalling slightly because I'm trying to get my board here, and my board doesn't. So hold on. Sorry, I don't actually know what's happening. Oh, but the question I was going to ask, this is a real question, because something funny is happening here. I think it's just temporary. But can any of you confirm or deny? Can any of you confirm or deny that your Google Classroom, like that your class still exists on your side? Did the class disappear is what I want, because it seems to have disappeared temporarily. And I'm not panicked. I'm sure it just like went into archives or something, but on my side, your class disappeared. So I just want to see if it's still there it still exists. Okay, great. Thank you. Thank you. All right. And that's points for answering. Thank you. That's awesome. Okay, so something funny is just happening on my side right now that I would like to have a board to teach. Oh, I know what we can do. If I can't, I will, if this doesn't work, I will give up on it in a second. I'll teach anyway, but it is a lot easier to teach with a board. This is very strange. Huh. All right. I may have to reboot the board. Here's what we're good, but I would like to get to material. I know we mentioned yesterday we don't have an exam this week or anything like that, but I'd like to, progress the material. Also, I had big conversations with your lab instructors over the weekend. So, well, confirm or deny this, where I believe you guys in this section, are you up to lab? Well, maybe you should just, what's the last thing? What is due for you right now in lab, you guys? Like what report or what post lab 4? Okay, you're up to lab 4. Okay, all right. So if nothing, and I know that the labs are ahead of the lectures right now. I mean, that's supposed to happen, but I know that it may be happening a little bit more than is comfortable right now. Like I know you're doing things in lab that we've never talked about in lecture. I do get that the conversation board. Okay, thank you. Cool. Okay, so what I actually want to address today, if I get my board back, I'd like to try to help you with lab. You're up to post lab 4. So if I would like to address lab 4 today, if I get this board back. I mean, that's what I'm going to do, even if I don't get the board back. Hopefully, I will say things that are hopefully clarifying or and tie it to the material that we're doing, for our upcoming exam. When you say post lab 4, so that means it would not be too late, right, for me to help with lab 4. Like you have not, if you're up to post lab 4, that means you're not up to the formal report yet. So correct me if I'm wrong, but if I say things about lab 4 today, and if I answer questions in particular, it's not too late for that to be helpful, correct? Like that would still be helpful to your work for that. Yes, okay, great, thank you. And again, thank you for answering my questions. You're totally getting points for that. Okay, I'm going to reboot my board. This is really actually strange. I don't really know, like it's not even, but I'll tell you so we don't lose time. Yeah. Lab 4. So I'm going to start addressing lab 4 right now. Like I'm going to talk about lab 4 right now as though it were just a homework problem in the middle of assignment 4 or assignment 5 or something. Like it wasn't, obviously, it's a lab, but I want to address it as a problem because what it is, I mean, it's things that you have to do in the lab and you have to make measurements and all of this, but ultimately you take those measurements, you put them together and you're solving a problem. And the problem really is, if you think about it, the problem is given, and maybe you might want to start writing this down. Again, I'm trying to get the board going. I don't know what's happening, but here's the problem of lab 4 is diagram is, you have a lab table, right? You're shooting a marble off the lab table. You're shooting the marble, you're shooting a marble horizontally off the lab table. The marble is going through a photo gate before it falls off the table, right? It goes through a photo gate. It continues to go. It goes off the table in a horizontal fashion. You know the amount of time that it takes to go through the photo gate, or you read that that's the measurement you take over and over, and then you average them, whatever. You know the height of the table, right? So the givens are time through a photo gate, through a horizontal photo gate, height of lab table. You, by this point, presumably know or have discussed in other labs or are beginning to see here in lecture, you know the constant value of acceleration during free fall, right? Which we should address here. And that number is approximately 9.81 meters per second squared, right? Like the acceleration that things experience to a approximately constant rate when they fall to the ground is 9.81 approximately meters per second squared. So that's a given. The height of the lab table is a given. Is measured by you. The amount of time through the photo gate is measured by you. And from all that, you're trying to figure out, like the question is, how far away from the lab table will the ball land? I mean, in short, that's really the problem of lab 4. I mean, I believe, and correct me if I'm wrong, right? So, I mean, what makes it a lab is that a lot of the given information you're getting from measurements, and you have to measure somewhat reliably, and you have to trust your measurements. But once you make those measurements, then those just become given pieces of information in the problem. Like if it were a homework problem, they would have just been presented. The height of a lab table is this. The amount of time through the photo gate is that. The acceleration due to gravity in free fall is this. So how far away does the marble land? Like, that's the question. Oh, I'm sorry. There's one other piece of information actually that you need in order for it to all work. And in fact, I'm going to pause and ask you, just because I feel like this is like a little bit abstract until the board comes back. There's one piece of information that I did not mention just now that you do have to measure in order to put this all together and make it work. It's almost a choice. Like well, no, it's not a choice. Yeah, there's one other piece of information that I didn't measure. And I'm going to ask you in the chat if anybody to put it in. So I'll repeat the pieces of information I did give. I'm saying assume you use a photo gate to measure the amount of time that the marble goes through the photo gate. Assume that you measure the height of the lab table. Assume that you are told or you measured in some other lab like lab 2 the rate at which things accelerate constantly when they are in free fall. Assume that you have those 3 numbers. There's one other number you need in order to answer the question, how far away on the floor will the marble land? And by the way, let me repeat that to you, right? That is the question of the lab. I mean, it can be phrased different ways, but what you're trying to find out is where on the floor will the marble land if it was shot horizontally off a lab table from a given height. So I'm going to pause again to ask anybody for any kind of private or public insights or clarifications or answers in the chat. But the question I'm asking you for the moment to pause on is, I say you measure the height of the lab table. I say you measure the amount of time the marble takes to go through a photo gate, the amount of time it takes the marble to go through a photo gate. Like, that's what the photo gate is for. It's just a fancy clock, right? You measure the amount of time it takes the marble to go through. You measure the height of the lab table. You know, or have been told, or have previously measured the rate of acceleration in free fall. I claim that there's one other piece of information you need to measure or be told in order to put all this information together and get the horizontal target displacement on the floor. So my question for everybody to think about is, what's the other thing that you must have measured in the lab, or you must have to measure in the lab? What's the other piece of information you need in order to predict how far this marble is going to land on the floor? If what you have is time through the photo gate, height of the table, acceleration due to gravity, I claim you need one other piece of information. I'm going to pause for, okay. So I'm seeing something in the direct chat. It looks good. Okay, there's something in the direct chat. Very good thought. And I'm going to say right now to the person in the direct chat, really good thought. First of all, totally shows that, well, I'm going to read it. I'm not going to say the person's name, but if this is okay, the person in direct chat said, position that the marble needed to be shot from. That's a really good thought on a lot of levels, particularly as a forensic scientist, to say it that way. And it's very close to what I'm looking for, certainly very related. I'm going to say right now, that's not quite the right answer. And I want that person in direct chat to submit that for 11 points. Remember, so I'm admitting, I don't think that's right, but I think it's really constructive. And I think it's concrete enough and wrong enough that you should definitely submit, you private chat person should submit that for actually a bunch of things for points, but submit it as a wrong answer, please, for 11 points, because it's a gutsy wrong answer. But I'm going to read it again respectfully. That person saying the position that the marble needs to be shot from. Here's why I want to dwell on that for a minute. What's right about it or smart about it is he or she is definitely right that the information that we're missing, I mean, he or she definitely understands the question, which makes me feel relieved. Thank you. And again, my question to everybody else is what information left do you need in order to be able to predict where this marble is going to land? Now, what he or she is right about is there's something about the marble that we haven't said, or something about position or displacement, something measured in meters for sure. What she or he is right about is we need something else that's related to the marble or related to the shot that would be measured in meters. It would be measured in meters, so that we could put this all together. What I think he or she is getting at is that the photo gate, remember, it's a fancy device. It's a high-tech device. Honestly, when I was in college physics, we didn't have, well, we probably had them, but we didn't have them. But all it is, so it's fancy and it's hooked up to the computer and it's hooked up. Oh, and again, I keep forgetting, of course, your labs are simulations. I'm sorry. So maybe some of this is abstract sounding when I'm saying, obviously you're not in the lab room doing this. Thank you, COVID. But if you picture some sort of gate on a table that a marble is going through, the whole purpose of that gate is to tell us the amount of time it takes the marble to go through the gate. Let me be even a little bit more specific. Like what the gate does is it has an infrared laser beam, like it's shooting, there's a beam of light that's going kind of like a toll, like a toll on a highway or something, or like a radar gun from a police on the highway. There's a laser that's going from one end of the, and I shouldn't even say laser, like there's a beam of light. There's a beam of light going from one edge of the gate to the other. As long as that light beam is intact, I mean, and you can't see it, it's infrared, but it's a beam of light that's there. As long as it's intact, then nothing electronically or interesting is happening. But the minute something breaks that beam, right, just to explain to everybody, the minute something breaks that beam, interrupts that beam of light, the minute it's blocked, right, then the rest of the electronic circuit of which that beam is a part, the rest of the circuit dies. Like current is interrupted, the circuit dies. That sends a signal, in your case to a computer, but it could be to anything. It sends a signal that starts a stopwatch. Like I'm just breaking this down just so you can see that ultimately the simplicity of what we're using it for. When that beam is broken, a stopwatch starts somewhere, a timer begins, right? Then when the beam is restored, i.e. when whatever's interrupting it is no longer interrupting it. So picture like if a car were going through that beam, the minute the headlights crossed the beam and interrupted the beam, the stopwatch would start. But the minute the back of the car like exits from the beam and the beam is restored and nothing is interrupting anymore, then the stopwatch stops, right? I mean, and of course, in some ways, I assume you all know this, or I think you, right? But what does that mean? It means that the whole fancy rig of that whole beam is just a super, super, super precise timing device. Like we could just be using a stopwatch in our eye, it's just that we wouldn't get as high precision. So that beam is telling us how much time it takes for the marble to fully pass through the beam. That's what it's telling us, how much time it takes the marble to fully pass through the beam. So what's really smart about what private chat person wrote, like what he or she is saying is like, oh, all right, if that beam is just telling us like a time, what we really need to do with that is somehow like relate it to some kind of distance so that we can really get some sort of speed at which the marble is moving. Like, I think that's what that person's thinking, and I think they're right. Like the reason we're using the beam is ultimately to get a grip on how fast this marble is moving. In fact, I'll be more specific, how fast it's horizontally moving as it crosses, as it's about to exit the lab table and like fall on the ground. And so that person is right that what's missing is some kind of displacement or position or difference in positions measured in meters. That's what we need in order to actually get speed out of that time information. But that person, what that person said was like, we would need to know how far behind the beam we put the marble and let it go from. Very smart, because I could see that. Like if we know how far behind the beam is, it seems like, oh, then we would have like some sort of distance or displacement to divide by time and get a velocity. Very, very smart. Let me tell you all though, that the reason I just like tried to break down exactly what the beam is doing is if you really think about it, the information that the beam is taking can't possibly know or care how far the marble was away from it. Like the beam only knows what the marble does once the marble's at the beam. I mean, it doesn't like know anything, but physically the beam can only register any information about the marble like once the marble's actually there. So however far back we started the marble from sounds like it would be interesting, but it actually can't ultimately be relevant to any time that the beam is taking. I don't know if that makes any sense. So on the right track. But what I'm going to pause. I'm going to look in the chat. I'm going to look again at my board if it works. What I'm looking for is something like that, but so some kind of quantity measured in meters, some kind of displacement, but I don't think it's the displacement from the beam to some other marker, because I don't think the beam would know about that other marker. I'm going to pause. I'm going to look in the chat. Oh, okay. Oh, cool. Okay. Now I see something else in direct chat that's good, building off that, which is awesome. Again, that person, great that person said that. Something else in direct chat now. Oh, and it's beautiful. It's funny. It shows me. So what someone else wrote in the chat that is right. I mean, I sound like I'm about to be critical of it. It's right, but it also shows me that there's more than one option here. What someone else wrote in the direct chat is, so would it be the distance between the two photo gates? Yes, it would, if indeed you have two photo gates. And honestly, actually, you guys maybe have to tell me, when we used to do this lab for real in the lab room, we actually did used to give students a choice. It's true. Like some students would set this up with two photo gates. Some would use only one. There's advantages and disadvantages of both. The person in the direct chat who's saying that is absolutely right. If you actually have two photo gates, if you literally, if the marble goes through one photo gate and that starts a timer, and then the marble goes through another photo gate and that stops the timer, and then the marble like proceeds and falls off the table. If that's, and I'm literally asking, like maybe put in the chat, if that's how your rig was set up or your simulation, if there were two indeed photo gates, then I 100% agree. Then what we would need is the distance between the two photo gates. That is absolutely right. And I hope that makes sense to people. I'll also admit it's not the answer I was looking for because I wasn't picturing two photo gates. But yes, if you have two photo gates and the first one starts the timing and the second one stops timing, then yeah, absolutely. Then what you have is the amount of time it takes the marble to travel from one photo gate to the other. So as long as you know the displacement, the distance between those two photo gates, then what you absolutely do is divide that distance by that time. And what you would infer from that, or what you would know from that, is the horizontal, well, let me be very clear. You would know the average horizontal velocity of the marble as it cruised from one photo gate to the other. Like technically you would know the average, I shouldn't say technically, you would really know the average if you divided that displacement between two gates by the time between two gates, you would know the average velocity of that marble. And that's great. And the person who wrote that, first of all, they totally should submit it for points for all the different kind of points for answering my question, blah, blah. And I'll leave it to, I think it's right. But if you want an extra 11 points also for being, it's definitely right if you use two photo gates. If you actually only used one photo gate, you can also submit that one as wrong if you want an extra 11 points. No, that's weird. But yeah, and but I'm still, again, I'm gonna can you imagine, again, it's just so weird. Like I make myself so nervous teaching physics, and teaching physics is the one thing I know how to do. If I get this nervous doing this, can you imagine what I'm like doing things that I don't know how to do, which is everything else in life? God, I'm nervous because I don't have my board. My board is my security blanket. I'm like, I am to Linus as board is to blanket. So I'm going to check that in a second, but I want to add one more thing again to both direct chat people. One nuance of the lab, or one, like we're trying to figure out how far the marble is going to land on the floor, like how far away horizontally from the edge of the lab table is this marble going to land on the floor. What we're going to need in order to do that is the velocity with the horizontal velocity with which the marble left the table. Now, in principle, what that means is we need the instantaneous horizontal velocity of the marble applicable to the instant, the point in time and space when the marble was at the edge of the table and right about to go off. Like, I mean, again, I'm sort of talking in circles here, but it seems to me if we want to predict how far the marble is going to land on the floor away from the lab table, what we're really looking for in one big piece of information we're trying to put together is how fast instantaneously was the marble moving in a horizontal direction when it shot off the table. What I'm here to say now is as long as we get the average velocity of the marble as it careens along the table, we are going to believe that that average velocity that we get by dividing displacement by time is going to be more or less one and the same value as the instantaneous velocity right before the marble leaves the table. That is, they are not a triple equal sign. Average, you know, this is over and over again in this course. Average velocity does not mean instantaneous velocity. They don't mean the same thing, and they are frequently not the same number. They are not the same number as long as anything is accelerating. Is that if anything is changing its velocity at all, then at any given moment, what its instantaneous velocity is not at all necessarily what its average is for the whole. right? It's important to understand that, like for the exam coming up or whatever, there's not instantaneous does not triple equal sign equal average. However, sometimes they double equal sign equal each other. It's one of the point of one of our equations, right? This is one of those times. I believe that you can believe when you're doing this lab, when a marble is like careening across a table, and we're going to get more, I believe that it's probably careening across the table at more or less a constant horizontal velocity. If you're doing a lab write-up, whether it's post-lab or the actual lab write-up, that's a kind of thing you sort of have to say somewhere, maybe quickly, but you have to say it. Like you do a calculation to figure out the marble's average velocity, but then you believe that it's not changing its velocity because there's no reason for it. There's nothing pushing it against it or pushing it from behind. There's no forces. There's nothing influencing this marble as it just rolls along. It is just a Galileo's principle little machine there. You can believe that it's rolling along at basically one unchanging constant velocity. Therefore, it's like if you get a 90 on a test and a 90 on a test and a 90 on a test and a 90 on a test, then your average is 90. But also what you got on any given one test was 90 because they're all the same. You can assume that here. You can believe that here. So I'm going to pause again for a second. I'm saying, yeah, if you've got two photo gates, then what you need to do, one piece of information you absolutely need is the displacement between the two photo gates. I'm going to pause and ask while I check the chat again and check my board. What if you only have one photo gate? Then what measure? Then can you do it? And I mean, yes, you can. But what displacement would you measure if you only had one photo gate? A photo gate that acted the way I described 5 minutes ago. I'm going to pause. Okay, I'm going to give you time to think about that. I'm going to try this board again. But the question is, if you only have one photo gate, or you know what? Also, let me just ask, especially if people still aren't paying attention, could anybody, and it could be one of the two direct chat people that already, could anybody just tell me in the chat, like when you did this lab or this lab simulation, did you have one photo gate or two, or did you have a choice, or does the question even make sense? Oh, two. Oh, two. Oh, there were two for everybody. Oh, okay. Oh, well, then the person in the direct chat is totally right. Then I shouldn't even. Okay, that's cool. There were two. Okay, thank you both people. Do you want to think for a second what you would do if you only had one photo gate? Imagine if you had a photo gate. This is a good, and then we will move on because I think my board's about to work. But if you only had one, but people are with me so far, right? Stop me if this is all too abstract. But if you only had one photo gate, what displacement would you have? And if it, in other words, if it started the minute the front edge of the ball broke the beam, and then if that photo gate stopped, if the timer stopped the minute the back edge of the ball like exited the beam and the beam was restored, then what displacement would you use to do this if you only had one photo gate? And here comes the board. Okay. And here's the board. Well, okay. Now, I will tell you for whatever it's worth, and then let's go. I think if you only had one photo gate, you would measure the diameter of the ball. Does that make sense? Like the diameter of the ball, because the photo gate starts the minute the front edge of the ball breaks the beam. The photo gate stops the minute the back edge of the ball exits. So the photo gate starts the minute the front edge of the ball enters the beam. The photo gate stops the minute the back edge of the ball exits the beam. So if you think about it like Galileo's principle of relativity, if you think about how velocities are relative and how, from the beam's perspective, a ball is moving through it, but from the ball's perspective, a beam is just passing past the ball, right? Like from the sun's perspective, the earth is moving past it. From the earth's perspective, the sun is moving past the earth. From the ball's perspective, a beam of light is just going whoop and passing over it, and the beam is traveling the distance of the ball in that amount of time, right? Kind of interesting, right? So as long as you know the diameter of the ball and you divide that by the time through the beam, you never need to know like how big the beam is or anything. As long as you know the diameter of the ball And you don't need to know where the ball came from. If you, even with one beam, you can do this. And if you know the diameter of the ball and you know the time of the beam, the time through the beam, then you'll know the velocity of the ball, the horizontal average velocity of the ball through the beam. And then from that, you've got the instantaneous velocity of the ball right before it goes off the edge. Now, those are the facts that we're, so, okay. Okay, what I want to do now that we have the board, I'm staying on this topic. Like I'm sorry, that was like abstract in outer space, but I want to continue talking about this now more concretely, like what it is you're solving for in that lab. And I'm going to write it down as though, so I'm going to write it down as though it was a problem. I'm assuming you made, but I'm going to do it your way. Like now that two people, thankfully, or three people in the private chat have told me you had two beams, excuse me, yeah, two photo gates. Great. Okay, cool. That makes sense. So I'm going to do it as though you had two photo gates. Here's the situation. Okay. First of all, this is what I think, what I've drawn here, right, is I think it's the problem of lab 4, right? Again, what made lab the lab, even if it was a simulation, is you had to get some of this information from a bunch of measurements. And then you even had to put the measurements together, sort of in the way that we were just discussing, right? But once you took those measurements and you average them out, you put them together, what you end up is you have this information, right? You use a timer photo gate, and you use a ruler or something to put a displacement together with a time in order ultimately to get, oh, in fact, I'm sorry. You use a displacement, a horizontal displacement and a time, you put them together in order to get ultimately an initial instantaneous horizontal velocity, V not X, right? Like I'm saying, assuming you've done your measurements already, you ultimately, what you do those measurements for is so that you know the instantaneous rate at which this marble exits a lab table in a horizontal direction, right? And it does exit, let's also be clear, it exits the lab table in a horizontal direction. at that moment. It is going purely horizontally at some velocity. It is the beginning of the experiment from there on in. So call that a velocity, initial velocity, V naught, and I'm putting a little X beside it to make it clear that that is a purely horizontal velocity, right, initially. Then, of course, the ball like falls in a curve, it projectiles down to the ground. And what's also known is the vertical displacement of that curve. Why? Right? Like because you measure the lab table. And again, I'm not trying to pretend at all that the ball moves in a straight line horizontally or a straight line vertically. Like what the ball does is it goes something like that for sure, right? But what you know is the initial velocity, and you know the height, and what you're trying to find out is what that horizontal displacement X is at the end of the day, right? Like, and again, stop me, but I think that's the goal of the lab. What you're also told is, and you sort of figured out in lab 2 that we didn't really talk very much explicitly about here, you're told that when things fall, really the purpose of lab 2 is to discover that when things fall, or even better, when they free fall, when they are subjected to no influence whatsoever other than gravity, apparently objects not only change their position when they fall, they not only move and have velocity, but evidently they change their velocity as well. Like apparently when things fall, they don't just velocitize, they accelerate. But apparently, even though they have a velocity, right, which means they have a changing position. And even though they have an acceleration, which means a changing velocity, evidently, according to lab 2, evidently, they don't change their acceleration. Evidently, when things fall. So this is, by the time we get to lab 4, it's sort of a given, but it's something we've just been developing as a concept in lecture. So I want to, make a note of it. Evidently, free fall is a natural and very pervasive, very common, naturally occurring example of constant acceleration, right? We've been obsessing in lecture about constant acceleration, about changes that aren't changing, right? Like that's what constant acceleration is. Now, it's a kind of an abstract concept, but one of the reasons and again, from a calculus perspective, what we've really been talking about in lecture is situations where there is a first derivative of position with respect to time, where there is a second derivative of position with respect to time, but where there's no third derivative. That's really what we're saying in calculus language, right? We're talking about in lecture situations where something has a derivative and has a derivative of the derivative. Something that has velocity and has acceleration, but doesn't have a change in acceleration, what we would call jerk, right? All of our equations the 5 equations that we're developing in lecture are all about that type of restriction. There is a change, but there's no change in the change. Now that would be a very obscure, like, why would we obsess so much about like exactly that level? Why would we obsess so much about derivative number 2? One reason is because, in fact, that's what nature seems to provide for us around us all the time. When things just fall to the ground, apparently they manifest exactly that situation. So it's both very important to study, but it's also very easy to study compared to other things. I mean, it's accessible. So let me be clear about that for a minute. What I'm saying on the next page, I'm saying So let me back up for a second and make clear what I mean when I say free fall from here on in. When I say free fall is not the same word as fall. Fall generally means like moving down. Free fall doesn't have to mean moving down. Free fall is a situation. Free fall is a type of motion in which no influences, no external influences. What do I mean by that? I mean no pushes, no pulls, no what we would ultimately call forces. Certainly no contact from any other object, no external influences from any other object are acting. If a mass is in free fall, it means no other mass is touching it, no other thing is influencing it, nothing is influencing its motion at all, except for the ever-present influence known as gravity. What exactly is the nature of gravity? Yeah, right now, I don't know yet. I know that gravity seems, but I know I live in it all the time, as do you. Like, I may not know all the math of gravity yet. I may not know all the intricacies governing why gravity exists or where it comes from or how it acts. But what I know is that when you let things go, they seem to be pulled toward the center of the earth, everything around us, right? Like whether you do physics or not, we live in a physical world in which everything seems to be pulled toward the center of our planet all the time. That phenomenon, that just ever-present reality that we're living in, we call gravity. And I mean that seriously. Like, you know, people were dealing with gravity and taking into account in their predictions way for thousands of years, way before anybody had a deep, intricate mathematical like breakdown of exactly what they meant by that. So that's the state of our mind. Gravity is just this fact, this empirical strange fact that in fact is so strange we wouldn't accept it at all, except that it's totally common, that everything just seems to always be pulled toward the center of the earth. Now I'm saying if you take an object and you subject it to no influence other than that, in other words, you stop touching it, you let it go, you don't have to put a magnet to it, you don't tie it to a string. If you just let an object go and let it be influenced only by gravity, then we call that state free fall. Obviously, this is a case of free fall, but I'm saying that, well, you probably didn't see that. Well, you probably didn't see that either. Something going up without anything touching it is also known as free fall. Or the projectile, the object in your lab 4 that flies off a desk and goes in this strange parabolic arc, that is free fall. Free fall doesn't have to mean that you're literally moving down. You could be moving up, you could be moving sideways, you could be moving in any kind of combination of those directions, as long as nothing is touching you and nothing is influencing you other than gravity, we call that free fall. And what we believe about free fall, so next page. So again, this is all maybe a little bit of a sidebar, but and again, these are things that supposedly came out in lab 2, but I know who knows what it felt like when it was happening. I'm saying now, Okay, I'm saying now, when something is in free fall, it turns out, now this is not obvious, but it's true that when things are in free fall, they are pulled toward the ground, toward the center of the planet, of Earth, and by being pulled, they're therefore accelerated. They don't just move, they accelerate. What's the evidence for this? Well, the evidence for this is that if 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 there weren't acceleration, then when I let something go, like right now I'm holding something, it's got no velocity whatsoever. If I let it go, if it had no acceleration, then it would continue to have the same velocity, which is zero. So it would hover. The fact that things automatically go from zero velocity to some other velocity means that they're automatically accelerated. Indeed, they are, because they're being pulled to the ground somehow by this thing called gravity, which I don't know how it works, but it seems to be happening. Right? So when things fall, they do seem to accelerate. They get faster and faster when they're going down. They get slower and slower while they're going up, right? It turns out that there's a approximately constant rate at which that happens. That's really the purpose of lab 2. Again, lab 2, I mean, it seems very obscure while you're doing it. You're tying bolts to a string and all this. What you're really finding out in lab 2 is that while there is an acceleration due to gravity, there isn't an acceleration in the acceleration. And I don't want to get into the whole discussion right now, but the purpose of lab 2 is that the fact that the bolts end up being placed where they are in order to create a string that makes sound land in steady rhythm. The placement of the bolts on the string ultimately shows us the pattern of the bolts, ultimately shows us the pattern of this motion. The pattern is that there is a first derivative and a second derivative, but not a third derivative. In short, what I mean by that is if you want the bolts to land in equal time intervals, you find out that you got to put the bolts on the string at intervals aligned with perfect squares, right? I'm getting myself, but if you put the bolts at like 1 centimeter from the top and 2 centimeters from the top and 3 centimeters from the top and 4 centimeters, if you put the bolts in equal spaces, then if you take a string, for those people who never did this, if you take a string and you put bolts on the string and then you drop the string and you listen to the sounds that the bolts make when they hit the ground, if the bolts were placed in equal spaces, when they hit the ground, they won't land in equal times because the bolts are getting faster and faster as they fall. So if you put the bolts at 1 bolt at every centimeter and you drop the whole string and let the bolts hit the ground, you'll hear like da, 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 right? Because the bolts are going faster and faster. If you spread out the bolts properly in a certain pattern, if you make the top bolts farther and farther away from each other than the bottom bolts, then you can get an equal sound, but it has to be the right pattern of bolts. What is the pattern? The bolts have to be put at essentially perfect squares. You put the bolts at like 1 centimeter, 4 centimeters, 9 centimeters, 16 centimeters. And the reason for that is so that the spaces between the bolts are getting bigger, but always by the same amount. Like there'd be, if you could put them at like 1, 4, 9, 16, 25, then the spacing between the bolts is like 3, like 4 minus 1 is 3, 9 minus 4 is 5, 16 minus 9 is 7. The spacing between the bolts is like 3 meters, 5 centimeters, 5 centimeters, 7 centimeters, right? So the spacing are getting bigger and bigger. The bolts are getting farther and farther away, but by a constant amount. Like this one's 3 centimeters and that one's 5 centimeters and that was 7. It's always 2 centimeters greater than the last, right? So there's an increase, but it's a constant increase. It's a second derivative. The positions are at the perfect squares, like t squared, like the equation x equals 1 half at squared plus v naught t. It's all not a coincidence, right? What I'm saying ultimately is that lab shows that when things fall, they accelerate, but at a constant rate. Well, once you believe that, once you know that, you can use any of those equations to figure out what that rate is. And you may or may not have done it in lab 2, but it's easy to do. Once you believe that the equations of constant acceleration apply, then you can find out what the constant acceleration due to free fall is. That number, okay, I'm writing on the page here different ways. I want to emphasize from here on in, generally we call that number lowercase g. G is the constant rate of acceleration in free fall. We literally call it G because it doesn't matter really what the number is. The number is different depending on what units of measurement you use. And again, I just want to be clear. Not only does it not matter what the number is, don't memorize the number as such, and don't memorize like a negative sign or a positive sign, because let's be clear, what this number is the rate of change of the velocity. When things are on their way up, they're losing speed. When they're on their way down, they're gaining speed. What direction you choose to call this number totally depends on what direction you choose to call positive or negative. Like if you call up positive, then this number is negative. If you call up negative, then this number is positive. And you'll make your choice based on the problem. But anyway, what in meters, the rate of acceleration due to free fall is approximately 9.81 meters per second squared, meaning, which I might even add, which most of the time in physics, especially if we're not doing a high precision lab, most of the time it's convenient just to further approximate that as 10. You might say, wait, that seems like a lie. That seems outrageous. You just call it 10. Well, please remember that the 9.81 in the first place is an approximation. We're chopping off digits. This is a natural number that's occurring in nature. Nature never agreed to use meter sticks or inch sticks or yardsticks or mile sticks. Like those are all made up by us. There's no reason to assume that things that happen in nature are just going to fit perfectly into our measuring system, and they don't. The actual acceleration due to gravity in free fall is a number that goes on forever without repeat, like the number pi. So we choose to chop it off at certain digits. What number of digits do we chop it off? It just is a matter of what's convenient for us. So if we're going to choose to call it 9.81 in certain circumstances, it's just as convenient in others just to call it 10. And we frequently will. If we're in meters per second squared, the constant acceleration due to free fall is frequently just written as 10. Okay. If you're in feet per second squared, it's 32 feet per second squared. What does that mean? It means if you drop something like from rest in 1 second, it'll be going 32 feet per second. In the next second, it'll be going 64 feet per second of velocity. In the next second, it'll be going 96 feet per second, et cetera, right? If you want a different perspective on this number, you probably don't hear this a lot, but to me, it puts a lot of perspective. If you convert to miles per hour per second, remember the very first time we ever did acceleration, we first thought in those terms. Like if you want to picture these things in like car, highway, speedometer type terminology, when you drop something, within the first second, it's going 22 miles per hour. This is real. This is a conversion. If I just drop something and let it do free fall, within 1 second, it'll be going 22 miles per hour. Within the next second, at the end of the next second, it'll be going 44 miles per hour. At the third second, it'll be going 66 miles per hour, et cetera, et cetera. All of these are equivalent numbers, just depending on what units you're measuring in. So the point is not the number. The point is the concept that in free fall, acceleration is approximately a constant. Whatever we call that, whatever that constant is, we call it lowercase g generally. Okay? That's like known in our minds from here on in. Free fall is the most naturally occurring, common, familiar demonstration or arena of constant acceleration. So now back to the lab. Like here was the lab setup, right? What's given now is g in the y direction. So I should really say it like this. In other words, the acceleration in the y direction is a constant called g. The velocity in the horizontal direction, or the initial velocity, is measured as v naught x. In the lab table is height y. We're trying to predict x. Okay. Okay. What I want to say, I'm looking at the time. What I want to say is, and now again, some of you might have found this problem easy to understand in the lab. Some of you might have found it hard. This is the problem underlying lab 4. What I want to say now that I've set it up, like we have this given information, we have a goal. What we have at our disposal to solve the situation is we have now, as of last class, we have like 5 kinematics equations, 5 equations that govern our understanding of motion. More specifically, we have 5 equations that are all about constant acceleration, ultimately. Well, certainly 3 of them are very restrictively about constant acceleration. We have a group of equations that are often known as the constant acceleration equations. They're often also known as the equations for 1D kinematics. All of our equations deal with acceleration, velocity, position, and time in a one-dimensional situation, such as the very first homework we ever had in this class called one of the very first homeworks called number line, where a person was going back and forth like along a line, an x-axis at the front of the room. All of our equations assume one dimension of space, right? And we usually call that dimension x. This situation here in the lab seems to be dealing with 2 dimensions. That, I don't know, that may have consciously thrown some of you. It may be unconsciously throwing some of you, like without realizing you're being thrown. What's tricky at first about this lab is it looks like, for one of the first times, we're looking at a situation that exists in 2 dimensions. All of our equations each one of our equations deals with 1 dimension at a time. So what do we do? I'm just going to read this, looking at the time. I'm going to remind you, I'm reading this quickly. I'm going to remind you, GPR, Galileo's principle of relativity, the sort of concept that's driving us on the side while all these equations unfold. The concept is that the laws of physics hold true at all constant velocities, right? It doesn't matter if you're going 100 miles an hour in a particular direction, or you're going 70,000 miles an hour in another direction. As long as you're going in a constant speed in a constant direction, the laws are the laws are the laws. They don't change from one velocity to another. In other words, they don't change from one reference frame. It doesn't matter if you're the Earth comparing your velocity to the sun, or you're the sun comparing your velocity to the galactic center. Whatever your frame of reference is, the laws don't change. i.e. all velocities are relative. You have to choose a frame of reference because all velocities aren't relations, but whatever one you choose, as long as it's unaccelerated, is going to work for the laws of physics. So put another way, what is a reference frame really? What is a frame of reference? It's a coordinate system. As long as your coordinate system is not accelerated, physics will work. You have to choose a coordinate system, but whichever one you choose, as long as it's unaccelerated, physics will work. Therefore, what am I saying? What does this have to do with 1 dimension, 2 dimension, 3 dimension? It has to do with this. Okay, I know we have 8 minutes. Here's what we could call form 3.5 of Galileo's principle of relativity. Like we've had 3 forms of it so far. We're going to have a 4th form of it shortly, like in a week. You can call this one 3.5. This says, this is just another implication of Galileo's principle, but it makes it, what this allows us to do, the reason I'm making a big deal of this, and I know I'm sort of talking in circles today and I apologize, but this, what I'm writing right here, allows us to confront problems like Lab 4 and future problems that are coming. This allows us to now start extrapolating the 5 equations that we have. We have 5 one-dimensional kinematics constant acceleration equations. We're about to start moving more into the real world of 2 and 3 dimensions, right? Into the, we need to start taking our knowledge that theoretically only applies to like some particle going back and forth along one freaking axis of space. If we want to extrapolate or apply the knowledge that we have of 1 axis of space to 2 axes of space and 3 axes of space, right? The actual world, we need a way of doing that. I don't want to have a whole bunch of new equations. We're not going to have a whole bunch of new equations. What we need is a technique for taking the equations we have, the list of 5, and that list is not going to grow any further. We need a technique for applying that list of 5 to higher and higher dimensions. The technique is this insight. The insight is that any n-dimensional problem of physics any n-dimensional experiment, phenomenon, problem, whatever you want to call it, any n dimension, n could be any number, right? So take lab 4, for example. We have a two-dimensional situation here. We don't just have something going back and forth. We have something going this way and going down, right? It's happening in a plane. The issue, what I'm saying here right now is if we really believe Galileo, if we really get that the laws of physics don't change from one reference frame to another, from one coordinate system to another, they don't change from one axis to another either. Put another way, our one-dimensional equations, they only dealt, all of our equations that we have so far only apply to one axis, the x-axis, but there is no objective x-axis in space, just like there's no objective 10 miles an hour in space. X-axis is an axis that we draw relative to something else that we call the y-axis. We can choose to call this the x-axis. We can choose to call this the y-axis. Like you can choose to line up the x-axis with the Earth. You can line up with the sun. Space itself does not know or care. So those equations that we have, they apply only to one axis at a time, but they apply to any one axis we want equally and equivalently to all other axes. So if we have some physics that's happening in more than one axis at the same time, as you do in lab 4, what the real insight is to realize, oh, so wherever I wrote n right here on the page, just substitute the number 2 in your mind. Like lab 4 is a two-dimensional example. So what am I saying here? I'm saying, oh, a two-dimensional physics problem. You know what that really is? In fact, we don't need new techniques to solve a two-dimensional physics problem. We don't need new equations. A two-dimensional physics problem is really, in fact, two one-dimensional problems occurring simultaneously, yet independently. This is the insight. I know I have 5 minutes. I'm going to go back and solve the problem now in a minute. But from all time, no matter how complicated some problem looks from here on in, if we get two-dimensional problems or three-dimensional problems, what I want you to understand is any three-dimensional problem is really three one-dimensional problems all occurring at the same time, but not affecting one another. That's the insight here, that we can run all of our equations on each axis by itself. We can run each equation on its axis and assume correctly that what's happening on the other axes don't affect a first axis. Each axis is its own little world of physics that is not communicating with the other axes. The only thing that links all the axes together in a problem such as lab 4, what links them all together is that the motions in all of them are all occurring at the same time. So the one linkage among axes will be t. If you solve for, and this is what this is really trying to say, from here on in, it's a technique for solving problems. If you solve for t in one axis, you can assume that that t value applies to the other axes because everything is happening at the same time, but that's it. It's really like two different. So in this lab problem with 4 minutes, in this lab problem, so in order to solve this problem, right? I'm saying, so we got a ball that's going like this at some constant velocity. Okay, we've got some ball that's traveling horizontally at some non-changing horizontal velocity, whatever it is on average is the same as what it is at every point, which is the same as what it is at the beginning. And we've got something that's accelerating down at some constant value of acceleration. So we've got a constant velocity horizontally. We've got a constant acceleration happening vertically. It's like two different objects doing that, only they're doing it at the same time. That's what we have here. So in order to solve the problem, I've got 2 minutes, we can use one axis to solve for time and then plug that time into the other because they're happening at the same time. So So I use this equation in the y-axis where there's acceleration in the y-axis. But the initial velocity in the y-axis is 0, right? In the y-axis, we have a ball that just was dropped. It wasn't shoved down. It wasn't shoved up. It was going horizontally, but that's in the horizontal axis. In the y-axis, it was just dropped. So we have oh, sorry. Right, so we look at the y-axis and we get that the time that the ball must take to fall down is that. The amount of time that the ball takes to fall down is that. We got it from the y-axis. Then we go over to the x-axis, use the same time. So in the x-axis, x equals and whatever numbers were given, and these are all given, and this is it. I mean, I know it's 12:05, but I'm saying then you would plug in the numbers that were actually given or that you measured in the lab, and that's it. What's my ultimate point? Like, my point is you get the time from one axis and you plug that time into the other axis. Why are you allowed to? Because the two axes are independent yet simultaneous. If you, and again, you may, hopefully this is consistent with how you're thinking about the lab. I'm not saying you literally wrote it down this way or anything. I'm saying this is just, hopefully it's consistent and you see how it jives with what you're doing in the lab. But if you really understand everything I've just said, saying this is it, we're just about done. But notice this, if you really believe me and you really understand that the amount of time it takes the object to fall is the same amount of time as it takes to travel horizontally, then what that means, if you really look at the equations I just used, it means that I'm believing that if I just dropped an object from the lab table, if I just dropped it versus, and at the same time, you shot an object from the lab table, like the assumption behind what I'm doing here is if one of us dropped a ball from the lab table and the other one of us shot a ball as hard as we possibly could, it's huge horizontal velocity. So one ball just went doink and the other ball went and hit the ground. I am believing here, I'm assuming in your calculations to assume that they would hit the ground at the same time. That it doesn't matter it doesn't matter how fast you're going horizontally while you fall. If all objects fall at the same rate, then all objects fall at the same rate. And even if an object is doing something horizontally while it's falling, it's still going to fall at that same rate. And if I shoot a gun, if I hold a gun on the pitcher's mound and fire it while you drop a bullet from the same height, both bullets will hit the ground at the same time. That is what this assumes. If you believe that, then the lab makes sense to you. If you don't believe that, you want to think about it for a second and realize that that's an implication of how you're doing the lab. But okay, I went over time. Thank you very much for listening. That's it for today. I will stop the thing. I'll hang out for questions. But thank you, and have a good night. Thank you. Great day. Thank you. Okay, I'm going to stop. But I'm here for questions just in case. Okay. Blah, blah, blah.